Ever pondered the idea of time travel and if we could rewrite history? It's a concept that has captured our collective imagination for centuries, appearing in countless works of science fiction, from H.G. Wells' The Time Machine to the Back to the Future trilogy. Yet, it's not just a figment of our creative minds. Many renowned scientists and thinkers have also been enthralled by this concept, proposing a myriad of theories and hypotheses. Today, we're going to take you on a fascinating journey through some of these mind-blowing theories about time travel. We'll explore the realm of possibility, the science behind this complex concept, and the intriguing question: could we, given the right circumstances and technology, rewrite history? So fasten your seatbelts, or should we say, calibrate your chronometers. Prepare to have your mind stretched as we delve into the theories of time travel. Our first stop on this journey is with the genius himself, Albert Einstein, and his theory of relativity. This groundbreaking theory, put forth in the early 20th century, irrevocably altered our understanding of the universe's fundamental laws. At the heart of Einstein's theory are two main concepts: time dilation and space-time curvature. Let's break them down. Time dilation is the idea that time is not absolute. Instead, it's relative to the observer's speed and gravitational field. Picture yourself aboard a spaceship moving at speeds approaching the speed of light. According to Einstein, time would seem to pass normally for you. However, for an observer on Earth, your clock would appear to be ticking much slower. This is time dilation in action. Meanwhile, space-time curvature is a concept that comes from Einstein's general theory of relativity. This theory suggests that mass and energy cause the fabric of space and time to curve. Imagine a bowling ball resting on a trampoline. The weight of the ball causes the trampoline to curve downward, creating a dip. Space-time works similarly. Large objects like stars and planets cause space-time to curve around them, causing what we perceive as gravity. Now, how does all this tie into time travel? Well, some physicists argue that if space-time can be curved, then it could, in theory, be twisted and folded to create shortcuts through time and space, also known as wormholes. However, this remains purely speculative for now. Additionally, the concept of time dilation suggests that time travel into the future could be possible. If one were to travel at near light speeds, they could return to find Earth's future significantly advanced. While Einstein's theory doesn't explicitly allow for time travel, it certainly sets the stage for further thought. It pushes the boundaries of our understanding, inviting us to imagine what could be possible in this vast and incredible universe. It's a reminder that, in science, even the wildest ideas can spark revolutions. Next, we venture into the realm of wormholes, a fascinating concept beloved by many science fiction writers. Wormholes are theoretical passages through space-time that could create shortcuts for long journeys across the universe. They are predicted by the theory of general relativity. But don't get too excited just yet. While wormholes are interesting features of a mathematical model, no one has ever observed one, and we're not sure they actually exist. But let's imagine for a moment, if they do exist, they could provide a means for time travel. Here's how. A wormhole is like a tunnel with two ends, each in separate points in space and time. If you could enter one end, you could pop out at a different time as well as a different location in the universe. Think of it like this. Imagine you're trying to get from one page of a book to another non-consecutive page. Normally you would have to flip through each intervening page, but a wormhole would be like a bookmark that lets you instantly flip from one page to another. In this analogy, the pages are moments in time. So, a wormhole could potentially allow you to flip from one moment in time to another. But there's a catch. Theoretical physicists predict that wormholes would be highly unstable and would likely collapse instantly after forming, unless they're propped open by something known as exotic matter. This is a hypothetical type of matter that has negative energy density and large negative pressure. And again, we don't yet have any evidence that exotic matter exists. So while the concept of wormholes and their potential for time travel is fascinating, we're still a long way from being able to use them to hop across the universe or journey through time. But who knows what the future of science will bring? Wormholes, while theoretical, open up a world of possibilities for time travel, don't they? As we delve deeper, we encounter the puzzling world of quantum mechanics. Quantum mechanics, the science of the very small, takes us on an entirely different journey through time. It deals with particles so tiny, their behavior seems to defy the laws of physics that we're familiar with. In the quantum realm, particles can exist in multiple states simultaneously, a concept known as quantum superposition. Imagine a quantum particle as a time traveler. It exists in the present, but also, strangely, in the past and future. This is not just a theoretical idea, it's been proven in experiments where particles seem to know their future state and adjust their past accordingly. This mind-bending view of time and its fluidity is central to the theory of quantum mechanics. It's as if time in the quantum world is not a one-way street, but a bustling roundabout where particles can move forward, backward, or even stand still. Now, how does this relate to time travel? Well, if particles can move back and forth in time, could we, made of these particles, do the same? Theoretical physicist Richard Feynman once suggested that perhaps all particles are just one particle, bouncing back and forth in time. This idea, though controversial, is a testament to the bizarre possibilities the quantum world presents. But before you start drafting your time travel blueprint, remember that quantum mechanics is notorious for its paradoxes. The same quantum superposition that allows a particle to be in multiple states simultaneously also means it's impossible to predict with certainty which state we'll observe. It's as if the universe is playing a high-stakes game of roulette, with time and reality as the chips. Furthermore, the scale at which quantum mechanics operates is incredibly small. So, while a quantum particle might time travel, scaling that up to human size presents enormous challenges. Quantum mechanics, as perplexing as it is, opens up a new dimension to our understanding of time. With its strange rules and paradoxes, it reminds us that the universe is far more complex and interesting than we can ever imagine. Now, what if you could travel back in time and change something? This brings us to the grandfather paradox. The grandfather paradox is a fascinating concept that challenges the very idea of time travel. Picture this: if you could travel back in time and, let's say, accidentally prevent your grandfather from meeting your grandmother, you would never be born in the first place. But then, if you were never born, how could you travel back in time to prevent your grandfather from meeting your grandmother? It's a classic paradox, a self-contradictory loop. It's a thought experiment that questions the idea of changing the past. If the past can be changed, it would create a ripple effect, altering the present and future in ways that could lead to inconsistencies, like our grandfather paradox. This paradox suggests that time travel could be inherently paradoxical, thus potentially impossible. As you can see, the grandfather paradox presents a compelling argument against the possibility of rewriting history, the Novikov self-consistency principle. From the perplexing grandfather paradox, we move to a concept that attempts to reconcile the inconsistencies that arise with time travel, the Novikov self-consistency principle. Named after the Russian physicist Igor Dmitrievich Novikov, this principle asserts that if an event could cause a paradox in the past, the probability of that event is zero. In simpler terms, it's impossible for a time traveler to do anything that would prevent their travel through time in the first place. This principle takes into account the idea of a self-consistent solution, where any actions taken by a time traveler or an object that travels back in time were part of history all along. If we return to our grandfather paradox, according to the Novikov principle, something would prevent you from altering your grandparents' meeting. Perhaps you'd get distracted, or your actions would unwittingly ensure their meeting, maintaining a consistent timeline. It's an intriguing solution that allows time travel without the messy paradoxes. Yet, like many concepts in time travel, it's purely theoretical and opens up a whole new can of worms about predestination and free will. Is our destiny already written, or do we have the power to change it? This principle suggests the former, adding another layer of complexity to the enigma that is time travel. Emerging from the complex web of the Novikov self-consistency principle, we stumble upon an even more mind-bending concept, the multiverse theory. This theory, largely born from the strange world of quantum mechanics, suggests that our universe may not be alone. Instead, it could be part of an infinite number of universes, each with different outcomes of events. Imagine a vast cosmic quilt of universes, each patch representing a different reality. This idea introduces a fascinating twist to our time travel journey. If we were to travel back in time, it's possible we wouldn't be visiting our past, but the past of an alternate universe. This sidesteps the paradoxes we've been wrestling with. If you prevent your grandparents from meeting in this alternate universe, it wouldn't erase your existence because you originate from a different universe, where your grandparents did meet. It's like being a character in a book who jumps into another story. You can change the plot of the second book without affecting the first. This theory, while exciting, is still highly speculative and lacks concrete evidence, but it opens up a world of possibilities, transforming our understanding of time travel and our place in the cosmos. As we delve deeper into the mysteries of time travel, we find more questions than answers. But isn't that the beauty of scientific exploration? The quest for knowledge, the thrill of discovery, and the joy of challenging our understanding of the universe and our place within it. As we journey back to our own time, let's recap what we've learned. We've explored the fascinating world of time travel, a concept that has intrigued scientists and dreamers alike throughout history. Our journey began with the understanding of time as a fourth dimension, as proposed by one of the most influential physicists, Albert Einstein. His theory of relativity not only revolutionized our understanding of space and time, but also laid the groundwork for the possibility of time travel. From there, we delved into the mysterious realm of wormholes, a theoretical passage through space-time that could potentially allow us to travel great distances in the blink of an eye, or even move through time. These cosmic shortcuts, although not yet proven, continue to be a hot topic of research amongst physicists and astronomers. We then ventured into the quantum realm, where the rules of classical physics are thrown out the window. Quantum mechanics has suggested the existence of parallel universes and the possibility of time travel at a quantum level. However, these theories remain largely speculative and unproven. Our journey also led us to confront the grandfather paradox, a thought experiment that highlights the potential problems of time travel. If a person were to go back in time and prevent their grandfather from meeting their grandmother, would they cease to exist? This paradox raises profound questions about causality and the nature of reality itself. The current scientific consensus on time travel and the possibility of rewriting history is murky at best. While the theories we've discussed are intriguing, they are largely theoretical and lack empirical evidence. The idea of time travel presents numerous paradoxes and complexities that we are yet to fully understand. While time travel remains a captivating concept, whether we can rewrite history is a question that continues to challenge and intrigue scientists worldwide. Until we can definitively answer that, we'll just have to keep wondering and exploring the realms of possibility.